Okay, now this is the equation of the line. Do you believe me? Is that the line that goes to those 2 points? I mean, we've never even met in person, right? It seems like, how could you trust me, right? When we don't have that connection. You don't have to trust me. You can check it. How would you check this to make sure it really is the line we want? I mean, what if this is the question that's on the test to get into, Harvard Medical School, and you want to make sure that you got it right? How do you know this line goes through those points?
Do you use the same slope thing to check it out?
I mean, I could kind of rework the slope thing to verify that the slope is the same, but maybe I am not even sure if I remembered that slope formula properly, right? And then redoing it might just give me the same wrong answer. So you could look at the slope, but what does it mean for a line to go through a point?
Can't you use that point for the equation, like one of those 2 points?
Yeah, so if I take this point and put it into this equation, what should happen? Well, we can see what happens here. 24 minus 23 is 1. So what happens is it's a solution to that equation, right? Remember, that's what lines are, is really a set of solutions. So to go through a point really means that point should solve the equation, right? And we can check this one as well. Y is minus 5. So minus 5 should equal 6 times 3 minus 23. Minus 5 equals 18 minus 23, which is true. Minus 5. Oh, what did I wrote 25. I said 23. I know that. 18 minus 23, which is minus 5. Check. Right. So, whether you believe any of this stuff or not, this is the line that goes through those 2 points, because when I put those points into this line, they give me true statements. That's what it means for the line to go through those points. So that wasn't asked in the question. You can certainly trust your work, and you can trust me as well. But excuse me, you do want to remember, it's a nice thing to remember that that's what it means to go through a point. It's just that it makes the equation true. Now, the last part of your question, I think they sometimes ask you to put the equation in this form. So we typically like this y equals mx plus b. That's called the slope-intercept form. And I would always be happy if you put a line in the slope-intercept form. There's a lot of advantages to having it in that form, but this, and sometimes it's written like this, ax plus by equals c is another form of a line, and it has some other kind of properties. It can be easier to work with intercepts sometimes with this form, and some other things. So that's why they use it. All it is we just want to rearrange our equation and put the x's and the y's on one side. Excuse me. So for our equation, I would move this. Well, the easiest way would be to move the 6x over. Minus 6x plus y equals minus 23. In this ax plus by equals c form, we also assume a, b, and c are going to be integers, so no fractions. So if I had like 6/5, I'd multiply everything by 5 to clear out those denominators. I don't think they care if you have a negative 6x. I would probably multiply both sides by a negative just because I don't know, I feel more comfortable with that version. So this would be what they're looking for if they're asking it in that form. Does that help with that problem?
So if it's a if the slope is a negative, you switch it to a positive,
Well,
or
like right here, this step. Remember that's not actually the slope right now because it's not in the y equals mx plus b form. But I do think they prefer, I don't know that they would mark it wrong if you wrote it this first way. I don't think that's necessary to have the a positive, the coefficient on the x positive, but I like it better, I guess, with that. So that's how I sort of naturally would want to write it, would be that positive 6x minus y equals 23. Again, I will not be asking you those on the midterm or take home work or anything like that. I'm happy with the y equals mx plus b form.
and then on also on one of the assignment there was like, so they give you a graph and they already had the graph is already, they give you a graph and it's already like graphed, but they just wanted you to find, I believe they wanted you to find where like y-intercept or something like that, and it was kind of uh,
Yeah, I mean, if they give you the graph, then the y-intercept is just where that graph crosses the y-axis. So, and you can assume that those are at an integer, like this one's at -3, right? That's the y-intercept. I don't mind if you write it as a point or a -3. Right? Those are both telling me that that's the y-intercept. I'm not sure if that's exactly how the question would have been asked, but if you
I
don't,
think what she mean is they give you a graph, but then it asks for an equation. Write an equation for the graph.
okay, yeah, and that's a good question too. So let's say we have a graph and we want the equation. So whether or not that was the initial question, this is a good one to see. Anytime you want an equation, that's the same thing as what we started with up here. It's getting to be kind of a mess, right? But it's this, right? I want to find the slope and then I want to find a point. And if I have those two things, I can come up with my equation. So I can ask these in all kinds of different ways, but it still always comes down to what's the slope and what's a point. So if you have the graph, you just want to pick any kind of convenient points. And I put them on the intercepts just because it's easier for me, because my kind of mediocre graph. But if it's on a grid, you could just pick any value where the line is clearly touching a point that you know. And then in this case, I know the y-intercept, right? It's -3. So I don't actually even need to solve for b because I happen to know what b is. Sometimes you won't know exactly what the y-intercept is. And then the other component is I need the slope. And as long as I have 2 points, the easiest thing is just to count. So that's up 3 and over 4. So that's going to be a slope of 3/4.
How'd you get up 3/4?
So I'm always, whenever I'm looking for slope, remember is the rise, which is the vertical distance here. And I sort of scratched it out there, right? But that vertical distance is 3 units divided by the horizontal distance, which was 4 units. And it's just counting on that graph. You could also calculate the slope. You know, my other point here is 4, 0. I know the x-intercept. And so if I don't want to do that counting, I can also use that formula. Y2 minus Y1. So that's Y2 minus Y1 over X2 minus X1. And you can see that'll give you the same thing, just 3/4. It's a nice thing about lines is that you can solve the questions in lots of different ways. I'm quite happy with whatever technique you use, as long as it's you know, as long as it's a working technique. You could do either one of those to get the slope. Maybe there's some other methods I haven't thought of that you could also use, and that's fine too. So I don't tell you you have to do any of these line problems a certain way.
I have a question.
Yeah.
So why is it -3?
This. So remember in our form, y equals mx plus b. This b is always the y-intercept. From my graph, I happen to know the y-intercept was -3, so I could just fill that right in.
Okay.
And you can kind of see it anyway, because if I happen to know the y-intercept, that means x equals 0 and y equals the y-intercept. So when I put in x equals 0 here, right, whatever the slope is, it drops out, and I'm automatically going to get the y-intercept. So that works only when I happen to know that exact point. The first example we did here, I didn't know the y-intercept right away. My points were these. So in that case, I had to do kind of just a little extra step to solve for b. I had to put in one of the points and then solve for b.
Okay, that makes sense.
Mhm. So normally that's what you'll have to do. I would say overall, it's rare that you just happen to know the y-intercept with the problems that you'll see. These are all great questions. Any other questions from this?
Can we do
Um,
example?
one of the other one from last night that I was kind of struggling with was I think it says graph the piecewise defined fraction, I think.
Function?
So
Yeah,
like the function, it was basically g parenthesis x parenthesis close, and then it has like equals and the like a parenthesis
Yeah,
squiggly line
yeah.
thing. So it was like -2, and then if x greater than 0, and then -5 if x greater less than equal to. Okay, so -2 if x less than or equal to 0, and then negative, and then underneath it says -5 if x greater than or less than 1. And like I was trying to, and then it wanted you to put in like a point or something, and that was what I was having problem with.
Okay. Were there any other questions about this problem here before we move on? And we can jump back into lines too later on, but any other questions about this one?
I have a question.
Yes.
So if it's rise over run, if the slope is negative, do you go down
Yes,
and over?
that's a good question. So yes, now there's two ways to look at the slope here. So this is a positive slope, right? 3/4.
Yeah.
But if I start here, well, then my rise would be -3, right? To go from this point to this other point, I'd go down 3, which is -3, and then I go left 4 units, which would be -4. But notice if I look at that ratio, -3 over -4, that also equals 3/4. So,
Okay.
so it turns out you can kind of go either direction and you'll still get the same value. Now, your question was, what about if we have a negative slope? So here, again, I can start at either point. If I start here, then my rise is 2, but my run is -2 because that's over to the left. So that would be 2 over -2. A positive over a negative will be a -1. So for a negative slope like this, either the rise or the run is negative, which is going to make your slope negative. So negative slopes are always going down from left to right. Positive slopes are going up from left to right. Does that answer that question or?
Yes, thank you.
Okay, great. Okay. Let's take a look at this piecewise function. Let me rewrite it because it's kind of messy.
There's a equal to under with the 1.
With the 1.
Yeah.
Okay. So a function, remember, is a relationship between inputs and outputs. The inputs are the x values, and the outputs are the y values. Okay, and when we have a function, what that means is a function has one output for each input. If y, let me say, if we have a function then we often let y equal f of x. So what this notation, this f of x notation means is that we're working with a function and the y values come from the x values. So that's the important relationship, is that you start with an x value, and if it's a function, it should create one y value from that. We cannot have a situation where, maybe we have these x values and we have these y values. We can't have an x value that goes to 2 or more y values. This would be not a function. Each x value can only go to one y value. Now it's
What about the
fine.
y?
It's fine to have x values all go to the same y value. This is okay, right? Function.
I have a question.
Yes.
You said that x cannot be a go to y 2 times, but y can go to x 3 times, right?
Yeah, a single y can come from multiple x's. We
How?
think of,
Is it like a normal function or
well, we think of like a function starting with the x's, the inputs, and then going to the outputs. So when you sort of give it an input, often it's a number for us, but it could be other things too. If you give it a number like 2, you should get an output, maybe 7. But it shouldn't be the case that if you give it 2, you get an output like 7, and you also get an output like 5. That's
Oh.
not a function,
Okay.
and it's sort of not how we like the world to work, right? We would like it if you do step A, that it results in step B, right? We don't want it to do different things, okay? But it is okay, like you said, if different X values all go to the same Y value, that's fine, as long as they go to one Y value. This is where our English language is a little imprecise.
Okay. I understand you now.
Okay, that's an excellent question, because that's really the key, that's the core of what a function is. So there are lots of different ways of defining functions. We can have these kind of maps, like I drew here, these little circle pictures. We can also just kind of list a bunch of ordered pairs, X's and Y's, or we can have a kind of equation like we have up here. And this is a kind of special type called a piecewise function. Piecewise. And what that means is it's defined in different pieces. And the way to read this is that this is a function, and the Y values are determined from these formulas here, right? Sometimes this function is -2, sometimes this function is -5. It cannot be both values, right? Because that would be a problem. That would like be this situation, not a function. It has to be one of these or the other. And the way I choose which value or formula it is from this. So if I put in -6 to my function, so this is the input here. That's the X value, the input. I want to figure out what the output is. The output's determined by this formula. And since the input is less than 0, it's -6, I choose this output, -2. If you give me a different input,
Where did you get -6 from?
oh, I just made it up. I mean, you can give any input you want. So the question will typically, I mean, there can be lots of different questions about it, but often they'll tell you what is f of some number. So like the second question is, what is f of 0? So if I input 0, which formula do I use? Zero is less than or equal to 0. So that tells me I use the top formula, and the top formula is just -2. You could come up with a graph for this if you wanted. F of -6 is -2. A small graph here. F of 0 is also -2. For any X value that is less than or equal to 0, it's going to be -2. That's what this equation or statement is telling me. So it's going to look like -2 for all of those values. When I get to 1, 1 is bigger than or equal to 1, so that's going to use my second formula here, which says every time I do that, I get -5. Should give myself a little more space, right? -5. And that's true for any X bigger than or equal to 1. So for all of these X values here, I'm always going to get -5. So this graph represents this function. It's pieces, right? It's sort of a Frankenstein function, like 2 pieces chopped up and put together. These describe the pieces, and these describe sort of the chops, right? The places where that is cut and put together.
So when you're graphing it, if it's like it's basically 2 is -2, -2, whatever. So if if on the y-axis, the y line it's -2, and if I go for the x line, the x part, would it be -2, -2?
Well, I mean, that is a point. So like if you pick a different X value, like -2, you'll also get -2. This says no matter what X value you pick that's less than 0, this function is always -2 for those values. So remember, a function is like a relationship, right? It's telling me what the outputs are going to be. And so here, this is the way of telling me that all the outputs are -2 if the input is less than or equal to 0. You know, piecewise functions are actually really common because there's a lot of things that kind of switch at a certain point, like well, my example, it used to be like cell phones, but now everyone has unlimited cell phones. But back when I was getting a cell phone, well, not even that long ago, you know, you would like get charged differently as soon as you sent like a certain number of text messages, right? It was like some arbitrary number, but they were free, so it didn't cost you anything. And then all of a sudden, when you sent like 500 or something, it'd bump you up and it would start charging you like 10 cents every text message. And I don't know if there was a third tier at a certain point or what, but that's a piecewise function where it works one way up to a certain value, right? $0 up to 500, but then it works a different way past that value, right? It switches. And there's a lot of real world situations that sort of switch like that. Okay. Other questions? I know there was another one that we were
I have a
after.
question.
Yeah.
So I was doing the assignment and I have problem with a square root.
Okay. The
So
graph. The graph.
It's not a graph. Yeah, you also have to graph, but first you have to find the point. So it's like h parenthesis x's and then equals negative square root of x plus 7. Yeah.
And then maybe it's giving you something like this.
No, it didn't give me that.
What does it ask you to do?
Find a point and also graph.
Okay. So I mean, finding a point means kind of plugging in a value and seeing what the output is, right? Just like a line. So notice this is not a linear equation because it's got a square root in it. That changes it. So it's not a linear equation. But it is an equation, and so it has solutions. And so we want to know where those solutions are. What are the points, right? And so one way to do that is to just plug in a value and see what happens, right? So you can plug in lots of different values. It turns out that 2 is a nice value because 2 plus 7 is 9. And I know the square root of 9, which is 3. right? And so this is -3. And so that gives me a point, right? My X is 2 and my Y is -3. So that's 1 point on the graph.
I have a quick question.
Yeah,
So how do you know what points to have for your input, or it doesn't matter?
well, it sort of matters and sort of doesn't matter. I mean, really, any X value will tell you something. But some X values certainly are going to make your life easier than other X values. So this one was nice because I was imagining whatever I put in for X, I'd like to be a perfect square. That's why I chose 2, because that was going to give me 9, and I know the square root of 9. So that certainly made my life easier. Okay.
And you did that method to find Y?
Yeah, exactly. I pick an X, an input, and I put that into the function, and then the function tells me what the output is, which is the Y value.
Okay.
If I picked X equals 0, I'd get negative the square root of 0 plus 7, which is negative the square root of 7, and that's also a number. But and I could estimate the square root of 7 with the calculator, but it's not quite as nice, right? But that does work too. That's also a point. 0 is my X, negative square root of 7 is my Y value.
And you'd still get the answer right?
That would still be a point. I mean, if it asked me for a point, that's a point.
Okay.
So in that case, you could really pick a lot of different X values. Now, I don't want to pick like -10, because then I'd have -10 plus 7, which would be a negative under the square root, which is not a real number. So I can't do that. But any other value that doesn't give me a negative under the square root is going to give me another point, another solution, and a point on the graph. Okay. Now, that's one part of this. The second part of it, and this is something I want to talk about as well, is graphing nonlinear equations. So we know how to graph lines, hopefully, right? That's what we're talking about with slopes and intercepts and points. Okay, so that's great, and some of those same ideas apply here, except we don't always know what the equations look like. So what they do in this section, this is the last homework section here, is they give you some basic graphs. So f of x equals the square root of x is one of these basic graphs. Basic just meaning kind of like a building block. And if you start with the square root and you just plot points, so if I just pick x is 0, the square root of 0 is 0, and that gives me 1 point. X is 1, the square root of 1 is 1, so that's another point. X is 4, square root of 4 is 2, that's another point. If I just keep plotting all these points, I get a graph that looks like this. So moving forward, when we see the square root of x, we want to visualize this graph. And that's what we mean by like a basic graph, like a building block. Okay, so square root of x, you could certainly, if you forgot it, if you fell and hit your head and had to start over, you could just plot the points and get there. But we want to know it at this point because we'll keep seeing it over and over again. And there's a couple others that they do. Absolute value of x is also a very popular or common one, I should say. Maybe it's not popular. It's just common. Okay, it looks like this V.
The graph on the left, did you just pick whatever point you wanted to pick, or
So kind of same as before. Yes, I picked whatever points, but I was also picking points that gave me nice square roots because I'm sort of lazy, right? And I don't want to find the square root of 3. But that works too. That's also a point. You know, if I found all those other points, they would just keep filling in this graph. And so if you want to do that, you can certainly check that and sort of see how that fits together, but you're perfectly welcome to just sort of trust me and say, okay, I guess all those solutions are going to fall in that pattern. So yeah, I think that a lot of students, a couple of these questions have been a little bit like kind of, can you just do anything? Which maybe feels like not math like, right? That you're very constricted in math. And yes, you can just really choose any point. You can really do almost anything you want to in math, to be honest. I mean, I guess that's not true, but you know, like here is an equation. If I want to, I can multiply both sides of this equation by 5. I can add 17 to both sides of the equation. That's all fine. Now, those steps aren't moving me towards the solution in this case, but I can do that. That doesn't change the equation. That keeps things fine. So I think sometimes we feel like there's only kind of one thing to do here. There's actually lots of things you can do. It's just there's only one thing that kind of moves you in the right direction. With these graphs, you can pick any kind of X you want, but certain values are going to make things easier for you than others. When I do X squared, and again, if I plot those points, I get this kind of curve, this little, it's called a parabola. And I don't want to spend a lot of time just plotting points because it's not that interesting for anybody, I think. Well, I mean, it's sort of interesting, but it takes time, and that's not really the point here. The point of this section is to say, these are graphs that I know. And then what we're going to look at are what are called transformations of these graphs. And the idea is, what happens if I run into the graph f of x equals the absolute value of x plus 2? And we should be thinking like, boy, that's almost like this absolute value graph, but not quite, right? It's got this plus 2. So the question is, do I have to start over and start plotting points again? Or can I use what I already know about the absolute value to come up with this new graph kind of directly? And it turns out we can. What happens is the plus 2 here on the outside, it just adds 2 to every y value that I have up here. So instead of this point being right at 0, 0, it's going to move up 2 units to right there. And the whole rest of the graph, every other point, I'm going to find just like I did up here, but then I'm going to add 2 to it. And so I'm going to end up with the whole graph just shifted up 2 units. And I don't always know how students feel about things, but I feel like this is awesome because I don't really love plotting points. I got to find a whole bunch of points and I don't know which the easy points are. It's hard to do. But if I know what the absolute value of x is, then it turns out by looking at it this way, I know what the absolute value of x plus 3 looks like, or the absolute value of x minus 10 looks like, or anything plus or minus a number, it just shifts it up or down. So that all of a sudden takes me from one single graph to, well, let's be honest, infinite graphs, right? I can add whatever number I want to the absolute value of x, and I know what that new graph looks like. And that's true not just for absolute value, but square root of x, x squared, any other new graphs or any other graphs that we might see. Okay, and so that's our one of our transformations. It's called a vertical shift. It just moves the graph up or down. Questions about that one? We're not looking for a super precise exact graph here. We're looking for the general shape that's correct, and maybe where the most sort of important feature is, right? That one should be located. Everything else is, you know, if your graph looks like this, that's fine, right? We're not worried about that at this point. We're worried about the general shape and its location. Okay, so here's a different example. It looks kind of the same, but it turns out it's not. Well, I mean, I guess it's related, but the +2 here is not done after the fact, right? In the first example, the +2 was added on after I did the square root. So I just took the original square root function and just could move it up. But here, what's being changed is really the x. And I like to say, and you'll see if you look at the videos, that that's like an inside. I'm changing it inside or before I take the square root. And what that's going to do is that's going to create a horizontal shift. So rather than the one above goes up and down, this one is going to go left and right. And give me a second here.
We can't hear you.
Okay, you guys hear me now?
Yes.
All right, sorry, I have a little, I think I'm good for a little bit, but I have a little slight power issue, so I should be okay for a little bit. But if I drop off, I'll be right back. Okay, so getting back to this is a horizontal shift, so left and right. Oh, where's my camera thing froze up? Okay, let's try this again. Something. Give me a second. I was just like always in the most exciting part, right? We have a little glitch here. My little, somehow in my switching power around, I lost my camera. It's going to be a little bit of a problem. Okay, I'm back. All right. Great. Okay, so where were we? We were looking at this horizontal shift left and right. When I add 2, what that does is it turns out it moves the x values. It's a little counterintuitive, but it actually moves it to the left 2 units. Because now -2 is going to make this 0, where before 0 made it 0. So it sort of takes what was at 0 and moves it to the left 2 units. So watch out for that. If it's +2, it moves it to the left. If it's -2, it moves it to the right. At least in my brain, that feels, it's hard to, I know why it does that, but I sort of just think of it as doing the opposite is what helps me remember which way that goes. And the last transformation or type of transformation that we'll see is a negative. What this does is it takes every normal positive value and flips it. It makes it negative. And if it was normally a negative, it would make it a positive. So it takes everything and it flips it vertically. So my new graph looks like this. That's called a vertical flip. I did all of these with the absolute value graph, but I could have just as easily done it with the square root graph or the x squared graph. It all works the same way. The shifting, the flipping, the moving up and down. So I want to go back to our original problem here. And now hopefully we have a good strategy of how to graph this that doesn't involve plotting a lot of pesky points, right? This works, but it's cumbersome. And I wouldn't really know what the graph looked like very well anyway, since it's not a linear graph to start with. But now I know that this looks like a square root graph, which remember is this. The +7 is a horizontal shift because it's on the inside. And since it's a +7, that's going to move my original graph 7 units to the left. 1, 2, 3, 4, 5, 6, 7. So if I just had x +7, it would look like this. But I also have the negative. What does the negative do? When it's on the outside like that, it flips it down. So this graph is actually going to look like this. That's negative the square root of x +7. Right, this bottom half of that graph. Questions about that?
So x +7, 7 would turn into -7 when you plot your first point.
Well, I'm not actually plotting points to come up with this graph. I'm using the strategy that we just talked about with the transformations. So I'm starting with my original graph. My original graph looks like this. Square root of x. And I know that if I add 7 to the x, that's going to take my original graph and shift it 7 units horizontal. And then if I take a negative of that, it's going to take that graph and flip it down to the bottom. So it's going to look like that. Now, it turns out that this point that I had found earlier, that is on the graph 2 minus 3, or sorry, 2 minus 3. Again, my graph is, it's hard to tell exactly where that is, but that point is right there. And this point here, 0, negative square root of 7, it turns out that point is right there. So those points are on the graph, but notice the points don't really help me very much with the graph. The transformation gives me a very good sense of what that graph looks like.
Okay.
Okay.
But the final answer is that line that's going down, correct?
Yeah,
Not the
it's
one that's
just
going up.
exactly. It's just this part. These parts are just there to sort of
Okay.
see the process. Good question.
Yep.
You don't need to write those in there, but it can be helpful if you're doing a couple transformations to sort of do them in stages like that. After you do a couple of these, you might feel more comfortable like doing 2 at once, right? You say, oh, I know what the square root looks like, and I know this is how it's going to turn out. I strongly encourage you when you do these to say left to flip down. So you're just kind of indicating that like what you're doing, because what happens sometimes is people, I think they may know what they're doing, but they end up with a graph that does not look right, like their artistic skills or something got tangled up, and they end up with a graph that's not right. If I know that you have the basic shape of the graph and you know how it's been moved, I'm going to give you credit for having the right graph, even if it's kind of mangled. Okay, but if you don't tell me how the graph's moved and it doesn't look right on the sheet, then I don't know if you actually knew or not. So this is a very nice, this is what we would call kind of listing the transformations or saying what's been done to the graph. And I often ask you to do that when I have these kinds of problems. Other questions about this? And my lighting has gotten very dramatic, right? With this sort of I don't know, it's like some sort of movie scene or something. So I apologize for that. It's variable lighting here.
All right. Sometimes they put like it's the same equation, but then they'll add like +3 or something like that. So what would you do then?
So like at the very end, like
Yeah.
so square root of x plus 3, like that one.
Yep.
So there, because that's done after the function, that's going to be a vertical shift. So that's going to take my original graph and move it up 3 units.
Okay.
And if my original was that, the +3 just moves it up 3. Okay. Okay.